Welcome to the North Atlantic Fire Science Exchange's student webinar series. My name is Eric Evanson. I'm NAFSE's Science Communications Specialist. And the goal of our student webinar series is to connect students with the fire and forest community to develop positive working relationships, as well as sharing knowledge and information. And speaking of sharing information, why don't we go ahead into the chat and please put in your name and your affiliation so we can see who's on the call on the meeting today. All right, so welcome Katie and John and Michael. Maddie from the Forest Stewards Guild, welcome. We got Chris and Kathleen, Amanda, welcome everybody. Got William. Josh from the Green Mountain Finger Lakes region. Shlomaya Lightfoot. I hope I pronounced that properly. If not, I apologize, but welcome. John Mitchell is in. All right, excellent. We got a great turnout for today, and I'm glad you made it in because we've got an excellent presentation today. Today's presentation is forest structure drives fine scale variation in microclimate and fuel moisture in northern conifer forests. And our presenter today is Peter Breigenzer from the University of Maine. So a little bit about Peter. Peter is a graduate research assistant in the School of Forest Resources at the University of Maine. After receiving his bachelor's degree from the University of Montana, he worked 4 seasons on various fuels, fire, and forestry crews in the Northern Rockies and spent 2 years as a data analyst in an environmental chemistry laboratory. His current research examines biophysical and social aspects of how climate change impacts forest management. Now, the way it's going to work is Peter's going to go ahead and give his presentation, and we'll hold off any questions until at the end of the presentation. But if you do come up with some questions and want to throw them in the chat, again, we'll address those at the end of the presentation. And then we'll just kind of wrap up with a couple little final comments from our student webinar series. And then, so for right now, let's go ahead. I'm going to have Peter go ahead and give his presentation. And Peter, also, if there's anything else you'd like to share with the group during your presentation about yourself, feel free to go ahead and do so. So thank you very much today for being here.
Thanks, Eric. And thanks everyone for joining today. As Eric mentioned, I'm going to be talking about relationships between forest structure, microclimate, and fuel moisture at a couple of our study sites here in New England. Even though I'm the one presenting this research today, we have an awesome team that is all working together on this project. We have a couple professors from the School of Forest Resources at the University of Maine, Sean Fravor and Jay Wason. We have Mike Gallagher and Laura Conifer, who are both from the Northern Research Station. Mike is at the Silas Little Experimental Forest in New Jersey, and Laura is at the Penobscot Experimental Forest here in central Maine. We have Aaron Lane, who is with the USDA Northeast Climate Hub, as well as NAFSE, and John Neely, who's with the White Mountain National Forest. So I'm just going to talk a little bit about my background and how I got here, and then we'll work our way into the research project. So as Eric said, I'm originally from Montana. I got my bachelor's degree at the University of Montana, and I studied wildflower genetics there, which kind of got me excited about natural sciences, doing field data collections and looking at ecological and biological data. But during the summers in college and afterwards, I worked for both public and private entities, doing a variety of forestry and fuels work and fire work. Spent a lot of time on a chainsaw, spent some time on the fire line, spent some time on the back of a horse. And then some life circumstances led me to working in an environmental chemistry lab, where I spent all my time in a laboratory extracting samples or at my computer analyzing data. I was a water quality analyst, so I was looking for regulated contaminants in drinking water and groundwater. But all these experiences together kind of helped me realize that I enjoy working outside, I enjoy working with data and doing science. And that made me want to pursue a master's degree. So starting in the fall of 2021, I attended the University of Maine School of Forest Resources. I'm currently in the master's program here, set to graduate in about a month and a half. And the program here has been exceptional. I've been privileged enough to be part of an interdisciplinary fellowship program called the National Research Traineeship. It's an NSF-funded fellowship program that really focuses on giving students research experience across disciplinary boundaries. So I'm currently conducting one research project on social science, where I've been interviewing non-industrial private woodland owners throughout Maine on their views on climate change and how that affects the ways they choose to manage their woodlots. And I've also been conducting a project on the relationship between forest structure and understory microclimate and forest management, which is sort of the precursor for the project I'm going to talk about today. This has been in addition to plenty of other fun experiences I've gotten here in Maine. I've gotten to help out with teaching some chainsaw safety courses, got an experience working with drone imagery and how we can use that to better understand forest health. But this is all to say that fire was not a part of my original research plan here at the University of Maine until I discovered NAFSE. It was about a year into my master's degree that I first learned about NAFSE, and it was through a fire camp that they hosted in the New Jersey Pine Barrens that was focused at students and teaching us about fire ecology in the Pine Barrens and prescribed burning for fuels reduction in the wildland-urban interface. And after this New Jersey fire camp, I also was lucky enough to attend the first prescribed fire training exchange in Maine that occurred in Western and Southern Maine in the fall of 2022. And through all these experiences, I felt like I was able to access some of my prior experience of working for the Forest Service seasonally on fuels crews and fire crews, but also sort of weaving in my love of science and data. And through these experiences, I really learned that fire for me is kind of the ideal field for applying scientific questions to issues of management. So shortly after I attended that Trex last fall, I found a posting for a federal grant through the Joint Fire Science Program. For anyone not familiar with the Joint Fire Science Program, it's pretty much all the federal agencies that do any sort of fire work in the country come together for this program, and they fund a student-focused grant that they call the GRIN. And the goals of this grant are to, first of all, expose students to fire and fuels management, while also helping students develop a greater appreciation for the needs of managers, and then taking existing research that students are already doing and finding a way to apply them to issues of management. So this is where I took my existing study about forest microclimates and forest structure and applied them to the context of fire. And that's what I'm about to talk to you all about. So the conceptual space that we're going to be thinking about for this project is broadly conditions that contribute to fire spread. And this is obviously a very broad category, important for a lot of reasons, but two major applications that we can think about them in are the National Fire Danger Rating System and generally fire and fuels management. So both of these realms rely on inputs into the fire behavior triangle that you can see on the right of the screen, which are weather, fuels, and topography, where sort of ephemeral weather systems interact with the more or less constant topography and fuels on the landscape to produce a certain type of fire behavior. And the more ephemeral conditions that we're going to be thinking about in this project today are temperature, relative humidity, and fuel moisture. And while most fire behavior models assume that for a given burn unit or a given land area, they assume that those weather conditions are going to be uniform and constant throughout the entire landscape. Whereas we know that overlying forest structure and vegetation cover affects temperature, humidity, and moisture at the ground level. So if we can better understand the relationships between these factors, we can better understand predictions and expectations of fire behavior in order to better achieve burning objectives or to better understand fire risk for a given plot of land on a given day. So for the purposes of this project, when I talk about microclimates, I'm referring specifically to temperature and moisture that occurs beneath the forest canopy. And we can think of this in contrast to the macroclimate conditions, or what some people call free air conditions or atmospheric conditions that occur outside of the forest canopy, which is also where most of our large weather stations are placed, right? In fields or in tall towers that stick up above the canopy. And we know that tree canopies buffer understories from macroclimate extremes, primarily through intercepting solar radiation that would otherwise penetrate the forest floor. And by doing so, understory environments experience a certain level of temperature swing throughout the day. We can see in the graph on the right, on the x-axis, we have time of day over the course of a single day. And on the y-axis, we have temperature. And we can think of this in comparison to an open air environment. So in these diagrams, the little thing down in the middle of each panel is a microclimate sensor, sort of a depiction of it that we'll see the real ones later. But if we think of what a microclimate sensor in an open air conditions is experiencing, they're going to have much larger temperature swings throughout the course of the day. And this difference between microclimate and macroclimate is what is known as microclimate buffering. So on the left side of these daily temperature curves, we can see buffering of minimum temperatures, and sort of on the right middle, we can see buffering of maximum temperatures. And this is not necessarily a new idea. When we take fire weather measurements on the fire line and estimate values of fine dead fuel moisture or probability of ignition, there are adjustments that we can make based on whether the place that we're standing is greater than or less than 50% shaded. And that idea comes from this concept of microclimate buffering. In addition to microclimates, today we're also going to be thinking about fuel moisture, specifically surface fuels and dead surface fuels. And traditionally, fuels are broken up into different time lag classes. So we're talking about dead surface fuels. This is down, dead, and detached woody debris. And they're broken up into time lag classes. So we see 1 hour, 10 hour, and 100-hour fuels there that are based on the diameter of the wood, because we know that larger diameter wood often takes longer to both absorb moisture and lose moisture into the atmosphere. And there are lots of different classes of fuels, it goes up to 1,000 hour, 10,000 hour. I just provide a few here for context, but really in our research project, we're just focusing on 10-hour fuels. So woody sticks that are up to 1 inch in diameter. And I think this graph on the right does a great job of showing how different size fuels might respond to moisture. So on the y-axis of this panel, we have increasing moisture content as we go up. And on the x-axis, we have first a precipitation event and then some amount of days after that precipitation event. And if you see, the solid line on the graph depicts a large diameter log, where we can see that it might not even reach full saturation until after the rain event has ended. And it's going to take a long time for that large piece of wood to slowly lose all the moisture. And this is in contrast to fine woody debris, which is depicted by the dotted line on that graph. We could see it's going to quickly come fully saturated from a rain event, and it's quickly going to lose that moisture. And then sometimes starting a day or two after that rain event, it's going to slow, the moisture loss is going to really slow down, and that piece of fuel is going to start to come into equilibrium with its environment. So we can see here that two of the major factors that influence fuel moisture are precipitation and then the microclimate in which that piece of fuel exists. And I personally think that this concept of microclimate buffering and fuel moisture and how that affects fuel availability becomes really interesting when we think about long-term feedbacks between forest structure and microclimate and management on the landscape. So going back to this example of a microclimate sensor in a forest understory, if we have a given forest, it's the shading from those overlying trees are going to create certain type of temperature and moisture environment in the understory that is going to likely promote the growth and development of certain types of plant species or certain tree species maybe. But if we go and cut those trees, first of all, that's going to affect the light environment, obviously. Most silviculture in the Northeast is conducted to alter light penetration in the understory, but there are also going to be secondary effects on temperature and moisture in the understory. And this microclimate is going to be suitable for the growth and development of other tree species. And over time, as those trees grow up, they are going to, create their own shade and their own microclimate environments. And as we continually manage forests over the long term, and as they develop on their own, there are really complex and interesting feedbacks between how the plants both respond to the abiotic environment, but they are also affecting the environment at the same time. And then if we add another layer onto this, and we, instead of thinking about microclimate sensors, we put fire in the understory, now that vegetation is not only fuel for the fire, but that fuel is affecting the fire environment, and it is either casting shade or obstructing airflow through the stand. And so there are lots of complex interactions between fire and fuel and fire behavior. And this has been deemed by some researchers as the ecology of fuels. This comes out of southeastern research at the Southern Research Station in these really frequent fire systems, that see fire every 1 to 3 years maybe. And there are really interesting feedbacks that they see between the way that fires consume certain fuels and the way that they promote the growth of certain fire-loving species, and sort of the feedbacks and interactions that we see over the long term. So the overall goal of this research project is to understand the relationships between forest structure, microclimate, and fuel moisture. Our first research objective is to determine how forest structure influences microclimate and fuel moisture in the understory. And we're doing this across a large range of differently managed forest stands. And then we're also interested in understanding how microclimate alone affects fuel moisture. Because if we remember from the dry down graph, the microclimate in which those fuels exist is a big factor in determining how wet those fuels are going to be. So in our project, we conducted this at 2 different study areas in the Northeast, one in Maine and one in New Hampshire. If we see on the right side of this study map is the Penobscot Experimental Forest in central Maine. And this is a long-term experimental research forest that's managed by both the Forest Service and the University of Maine. They've been conducting experimental harvests here since the 1950s. And while there's not a huge history of fire on this landscape, although they have conducted a few prescribed burns in the past, the major value of the PEF, what we call Penobscot Experimental Forest, is that the long-term history of experimental harvesting has created a great diversity of forest structures and compositions that exist at fine scale relative to one another. They conduct experimental clear cuts to experimental selection cuts with everything in between, regular shelterwood, irregular shelterwood, different types of thinning, which has resulted in stands that are at all levels of development, as well as pure hardwood stands to pure softwood stands, and pretty much everything in between. PEF exists in the northern conifer system. So the dominant tree species that you'd see there are red spruce, balsam fir, eastern hemlock, with more minor components of northern red oak, white pine, red maple, and birch and beech species. And our other study area is what we're calling the Zealand site in the northern White Mountains of New Hampshire. And this Zealand is located just off of Highway 302, kind of near Twin Mountain. And it's managed by the Forest Service. And this is, while there is not also a huge history of fire at the Zealand plot, it is on the docket to be burned this year, which is why we chose it as one of our study sites. And Zealand is still fairly conifer dominated, but also has a little more influence of your northern hardwoods. So there's white and red spruce there and balsam fir, but also larger components of black cherry, aspen species, sugar maple, in addition to red maple, and birch and beech species. So at each of these plots, at both of our study areas, we put microclimate sensors out. So in that picture on the left, up in the cup on that stake is a microclimate sensor suspended. The sensors themselves are about the size of a quarter, and they measure temperature and relative humidity every hour. And in addition, at the center of each plot, we had fuel moisture arrays where we put out pre-made fuel moisture sticks and measured their moisture throughout the year. Before we put these sticks out in the forest, we dried them in an oven till they were bone dry, and we took the dry weights of them so that when we actually went out and weighed the sticks at their wet weight in the woods, we can immediately calculate the percent moisture content. And so the second photo here is just an example of our mobile fuel moisture analysis laboratory in which we can measure fuels in the forest. And so in addition to measuring microclimate and fuel moisture at these sites, we also did traditional forest inventories. We did 10-meter fixed radius inventories where we measured diameter at breast height and species of all trees in the plot that were greater than about the size of my pinky. And I also measured canopy openness at the center of each plot with a spherical densiometer. And for anyone that hasn't used a densiometer before, it's just a convex mirror, essentially, that you hold out in front of you, and there's a grid etched into it. And so it gives you sort of a wide angle view of the forest canopy above you. And using that grid, you can tally how much of the sky is covered by trees and how much is not. And that gives you a measure of how open the canopy is. So we also measured forest structure at our sites using terrestrial laser scanning, or TLS. And TLS uses LiDAR to measure forest structure. For anyone not familiar, LiDAR stands for light detection and ranging, similar to sonar or radar, but instead of using sound waves and radio waves, it uses light. And here's just a little schematic of how the TLS unit works. It set it out on a tripod, and you literally just press a button once to turn it on, press a button again, and it starts to do its thing where it first takes a panoramic image in a 360 degrees around the entire plot, and then it shoots out millions of little laser pulses, and it keeps track of when each laser pulse was sent out and whether that laser pulse hits an object. And when it hits an object, the reflectance is returned back to the sensor on the instrument, and it gives you a basically three-dimensional view of your plot. And we can see that here. And while this 3D rendering of our plots are very cool to look at, we also need structural metrics that we can input into our models so that we can derive statistical analyses from them. And that's where Mike Gallagher's team at the Northern Research Station in New Jersey was super great. They lent us this instrument to begin with, and they also processed all of this LiDAR data and came back with hundreds of different structural metrics that are derived from this 3D rendering and can tell us more about the structure of each of our plots. So that's the first result that I want to talk about from our project today, is that TLS is pretty dang accurate at estimating forest structure. So for the next few slides, I'm going to show a lot of our data, and I'm mostly going to be showing linear regression plots. So this first one here, if we first look at the x-axis, that is a LiDAR-derived measure. And then the y-axis is showing canopy openness as measured with the spherical densiometer. So each point on this graph refers to one forest plot that was both measured traditionally and scanned with a TLS. And we can see that this LiDAR-derived a measure known as like percent gap, which is essentially how much of the plot is open on top and how much is not, which obviously corresponds pretty closely to canopy openness, is a pretty good predictor of canopy openness. And we see in the upper part of the plot there, we have an R squared of 0.89. And R squared is a statistical measure that tells us how much of the variation in our X variable, so percent gap, how much of variation in that explains the variation in our Y variable. So R squared of 1 would be a perfect relationship where all those points were lined up directly on that regression line. But 0.89 is still a pretty high R squared. In addition to canopy openness, we also modeled basal area using the LiDAR data. And the best predictor that we have here corresponds most closely to the 35th percentile of the height distribution of all returns at a plot. So really it's like the lower third of the forest, and that makes sense for predicting basal area because that is where all of the tree trunks are. And we can see here there's a really tight relationship between this predictor and basal area up to about 100 square feet. And then as we get higher than that, the relationship breaks down a little bit with the R squared of 0.76. And finally, we modeled trees per acre, that's TPA on the y-axis. And our predictor variable for this is kind of similar to basal area, but slightly different, where it's the percent of all returns that occurred in the 1 to 3 meter height layer, which again makes sense for predicting trees per acre, especially because we measured both overstory trees and saplings at our plot. So that's going to capture a lot of the variation in those trees. And we see a R squared of 0.78 there. So now thinking about the microclimate at our sites, indeed, the Penobscot and Zeeland sites have different climates. And this is likely driven by Zeeland being nearly 1,000 feet higher in elevation than the Penobscot site. So we see on the left on the map there, just reminding you all which site is which. And then the top graph we have here is of daily maximum temperature. On the x-axis, we goes from early July to early September. And the solid line refers to the Penobscot experimental forest, and the dotted line is Zeeland. And these are daily max temperatures averaged for all of our study sites. And then on the bottom graph here, we have, again, early July to early September on the x-axis, and our primary y-axis is daily minimum relative humidity. And we can see there that the dotted line of Zeeland is typically higher for minimum relative humidity than the Penobscot site. And this makes sense because we know that relative humidity is driven a lot by temperature. So if you have hotter daily maximums, you're likely to have lower daily minimum relative humidities. And the final part of this bottom graph, on the very bottom, we have precipitation bars. And you can see the scale for those are on the right side of the graph in inches. And while we didn't measure rain at our sites directly, these are taken from the nearest National Weather Service stations. And any of us who were in the Northeast this summer know it was a pretty wet summer. There weren't a lot of gaps in precipitation. It was nearly constant. But we were able to measure fuel moisture on some days where it wasn't actively raining. So you can see on the bottom there, for each site, we measured fuel moisture content one day at 2 days post-rain. And then at each site, we measured fuel moisture again at 6 days post-rain. And really the only window we had all summer for measuring 6 days post-rain came finally in September. So we found that forest cover indeed buffers microclimate, both the temperature and the humidity, and it increases fuel moisture in the understory. So here's another regression plot where on the x-axis, we have canopy openness, where 0% refers to completely closed canopies and 100% refers to completely open canopies. And on the y-axis, we have measures of daily maximum temperature. The y-axis is scaled in Celsius, and I threw in a couple conversions there for Fahrenheit. So it goes roughly from 70 to 90 degrees Fahrenheit on the y. And each point on this graph shows one forest plot and the average daily max temperature for that plot for the entire period from early July to early September. And we can see here that completely open canopies on average are nearly 8 degrees Celsius warmer than closed canopies. And despite Zeeland and Penobscot having different climates over the study period, this relationship holds pretty true in the relationship between canopy openness and temperature. And we see similar relationships between sites when we are looking at canopy openness and minimum relative humidity. So this middle plot, we have canopy openness on the X and daily minimum relative humidity on the Y. Again, each point is the average for each plot over the entire study period. And we can see from this plot that open canopy sites are nearly 25% less humid at midday than closed canopy sites. And finally, the third panel we have here shows canopy openness on the X and fuel moisture content in percentage on the Y. And interestingly, the two sites responded differently in their relationship between canopy openness and fuel moisture content. And we can see by the way those regression lines cross. And this is still ongoing research, and we have more analyses to do on this. I think this interaction might be driven by just a couple sites that responded in ways that we didn't quite expect, which is interesting in itself. But still, the overall takeaway from this graph is that open canopy sites are nearly 10%, have 10% lower fuel moisture at midday than closed canopy sites. So another big takeaway from our work so far is that microclimate variables in general are better predictors of fuel moisture than forest structure variables. This is not terribly surprising. Going back to our graph of how different fuels dry out, we know that once we get a couple days after a precipitation event, the microclimate in the environment in which those fuels exist is likely going to be a driver of moisture of those fuels. But here's a few examples here. I'm going to show outputs from models using microclimate variables, as well as TLS-derived variables and traditional inventory-derived variables. So in the first panel here, we have daily maximum temperature on the x-axis and fuel moisture content on the y. And we can see that microclimate is a good predictor of fuel moisture in a couple ways here. So first of all, the R squared that we have reported at the center of the graph is an R squared output from all of our models that we ran. So for microclimate, we didn't just use daily maximum temperature as a predictor, although that's what I'm showing in the graph here. We combined temperature and humidity in a series of different models, and we took the average output from all of those models to get that R squared. And so we can also see in this plot of just daily max temp and fuel moisture content that the dots around each regression line are pretty tight and pretty closed in. So we can see the accuracy of that prediction there. And this compares to the center graph here, where we have a TLS-derived variable on the x-axis. Again, it's that percent gap that we saw before that's pretty correlated to canopy openness. And again, we have fuel moisture content on the y. And the R squared of 0.74 there is the average R squared from all of the models that we ran that used many different TLS-derived variables to predict fuel moisture content. And you can also see that the points surrounding the regression lines in this plot are a little more spaced out, and the relationships aren't quite as tight. And this goes further down the line when we look at our final graph that has basal area in square feet per acre on the x-axis and fuel moisture content again on the y. And we see our average R squared for traditional inventory measurements is 0.64. And the relationship between, even though we can see that increasing basal area indeed increases fuel moisture. If you have a denser forest, you're going to have more shading of those fuels, leading to higher moisture contents. The relationship between basal area and fuel moisture content is not quite as tight as, say, the relationship between daily max temperature and fuel moisture content. So just to conclude on some of these main points from our research at this point, when we're thinking about the relationships between forest structure, microclimate, and fuel moisture, we found that forest cover buffers microclimate, leading to more open areas having significantly warmer and less humid understories with drier fuels. And we also found that microclimate variables are the best predictor of fuel moisture when compared with forest structure variables, but forest structure variables are still fairly accurate. And we saw that TLS was a better predictor of fuel moisture than traditional inventory measurements. So what can we do with this information? Again, as I mentioned, this is still ongoing, and we have more analyses that we're planning to do with this data. But a couple things that I've thought of at this point are thinking about trade-offs between fuel loading and fuel availability. So we often think of areas with high fuel loading, lots of either down woody debris or, say, lots of small tree saplings that potentially are available to burn, might not always be because of the effects of forest structure on microclimate and fuel moisture. If you have a denser forest, there's more fuels there, but they might not be as available as fuels that are in a more open forest. And I think this finding really supports the idea of shaded fuel breaks that we might see in some areas, either on the edges of burn units or up against the wildland-urban interface, where fuels operations have gone in and removed a lot of the understory fuels and ladder fuels while trying to maintain a fairly closed canopy. So that's also reducing the fuel loading while simultaneously reducing the fuel availability by altering the microclimate and moisture content of those fuels. And then also thinking about the relationship between forest structure and fuel moisture. I would bet that most fire managers don't have the luxury of putting microclimate sensors out in the forest at fine scale, but they may be measuring forest structure or vegetation structure over the long term. So trying to think about how we can better understand the role of overlying forest structure and how that affects fuel availability, just to better understand fire risk and fire behavior in different burn units. So I really want to acknowledge everyone that's contributed to this project. First of all, the funders that allowed us to do this research, anyone that helped us with the proposal writing process that allowed us to access this funding, and finally, anyone who's contributed to the project or the field work at this point, folks that have helped with the conceptualization or literally helped with me collecting forest structure and fuel moisture out in the field, as well as processing the data. This is a huge team effort, and it couldn't be done without anybody on the screen. And with that, thank you. There's my contact info, and hopefully we can get to some questions.
All right. Well, thanks, Peter. Please leave that up on the screen for now in case
Sure.
anyone wants to make note of that. And I've got, I was looking for a question to ask you, but actually I went up more just a couple of comments. I'm thinking, so prior to me coming to NAFSE, I was with the National Weather Service for many years, also an incident meteorologist, and thinking about going out on wildfires and trying to work with the fire behavior analyst to understand, obviously the weather and the fuels to help with our fire behavior predictions. And so these are just kind of more comments, and I some of this data that you showed here is pretty eye-opening. And I'm just thinking, again, back being at an incident, trying to get the best feel for weather conditions and for fuel. And I thought it was an excellent point you made about the location of meteorological information from reporting stations versus the understory locations, where pretty much, whether any sort of reporting station is, like you said, is in the free air and not necessarily sampling there. And that can obviously have a huge difference. That difference was kind of unknown until what you were reporting here, which I think is just very eye-opening with the 8 degrees Celsius temperature difference with the canopy and the forest structure, the 25% relative humidity difference that can occur, and then even the 10% lower fuel moistures. I just think that's such a having that information it can be just very eye-opening, which will help anyone on a prescribed fire or dealing with wildfire to understand how that might have an impact on fuel moisture and fire behavior. Because I just think that when you're dealing with large wildfires, it's very hard to get a really good sampling of the fuel moisture over the entire area. And that can obviously have an adverse effect on fire behavior. And obviously now you're talking firefighter safety. And so I just think that this is very enlightening to know those type of differences. And hopefully fire practitioners can then have that in with their calculations and their thought process before putting together a burn plan. And maybe forest structure is a way to get that extra piece of knowledge to help them before they do put fire on the ground. So very, very enlightening and work that you have there. And right now would be a good time if anyone does have any questions, you can put them in the chat. I'm also going to make people available if they want to go ahead and turn on their cameras, which they can, or unmute themselves. You can go ahead and do that and ask a question as well. So again, I don't know, Peter, if you have any comeback from what I just had said. Otherwise, we'll just wait for some other questions in the chat.
Mm-hmm. Yeah, I mean, I will say we're not the first ones to show that the forest structure affects microclimates. So I can't take credit for that, obviously, but I do think if we have more ways to at least be able to quantify forest structure at fine scale throughout a burn unit or throughout, a chunk of land that is burning in a wildfire, it would greatly increase our ability to predict fire behavior. That's for sure. I think maybe some of these remote sensing technologies like airborne LiDAR, if you can fly over a plot or something and get those same kind of structures. Yeah, it's interesting stuff.
It just seems like sometimes it doesn't take much for something to go awry. And if you can just have all the available information in some way, shape, or form, that might just help the process.
Right.
Got a question here from Amanda. First, excellent presentation and research, Peter. Do you have, here it is. Do you have any thoughts on hardwood versus softwood fuel moisture, particularly shrubby scrub oak or even oak-dominated forest?
It's a good question, Amanda. I don't know particularly about the moisture content of different types of wood. We used pine, was the sticks that we put out in all of our plots was cut from the same type of pine. But in some of our other research, we thought of like the hardwood versus softwood dominated overstory obviously makes a difference, right? A lot of the burning we do in the Northeast is in tridodone and leaf off conditions in the spring or the fall, which allows, more solar radiation to penetrate the understory, which would then affect fuel moisture and microclimate. I'm thinking of shrubby scrub oak or oak dominated forests. Yeah, that's a really interesting point. I feel like in midsummer with broadleaf canopies might be shading even more than a conifer stand. But yeah, I have to think more about that.
Okay, thank you. A comment from John Neely talking about wish it hadn't been so rainy this summer, so that we could have burned the unit, before this presentation. Yeah, that would have been, yeah, it was pretty wet everywhere.
Yeah, unfortunately, that was the primary or the original goal of this was to, have the same outputs that we have now of the relationships between forest structure, microclimate, and fuel moisture, and then burn over those plots that we knew they had a certain microclimate and moisture throughout the season to see what is the relative influence of the microclimate and moisture on fire behavior in the moment. So flame length or rate of spread or something like that. Unfortunately, it doesn't always work out that way.
Does anybody else have a question or comment? Here's one from Neil Gifford, following up on Amanda.
Ooh.
Any thoughts on how fuel chemistry influences fuel moisture, which seems to be a major difference in fuel types?
That's a great question, Neil. Unfortunately, I don't know much about that, but I mean, we see, right, like certain fuels that have high oil contents, like in the leaves or something, there some days that's the only thing to burn if some of the woody fuels are more saturated. So they're definitely those are some interesting trade-offs between. So we were just thinking about, the moisture of like a 1-inch diameter woody stick. But on any given day, it would have been interesting to measure the flammability of that versus the flammability of a oily leaf or something. I like that.
Here's Joshua says, nice work, Peter. Here's a question from Michael Gallagher. What was the time comparison in collecting TLS data versus basal area data?
It's a good question. They were measured in the same month. I don't know exactly when, if that's what you're talking about, the timing over the course of the year. But we did our fixed radius inventory plots in July and early August, and then we scanned the plots in early to mid-August. So they were measured pretty similar time. Or how much time was saved. Oh my gosh. The TLS is so much quicker and easier. It's pretty crazy. I mean, to be able to calibrate it and compare it to basal area, obviously we still had to do our fixed radius inventories. But I'd say to do one plot in the traditional basal area inventory way was maybe 30 to 45 minutes. And to scan a single plot takes about 5. Thanks, Amanda.
Oops, I unmuted. I have a question actually for everybody that is a manager out there, and I know a few of you. I'm wondering how folks are taking this information in and how it's getting you thinking a little differently about your fire management in the ecosystems that you work in. I can call on individuals, but I'm sure your wheels are spinning after Peter's presentation.
Yeah,
Mike
this is
Gallagher.
John. Oh, sorry, go ahead.
No, please go ahead.
I was just gonna say quickly, one of the things that I was excited with this project is we can find it difficult to explain to other specialists and the public that just view fire as a single force that's going to go through the forest with exactly the same effects across the board. It can be hard to explain to them how different it behaves in these micro habitats, and being able to calm people down when we say we're going to bring fire through a riparian area or another habitat where they think it's just going to be destruction. And this helps explain to them your flame lengths, your rates of spread, your fire intensity is going to change drastically as it moves through these different habitats.
Did you call on me, Amanda? I thought you were saying my name.
Yes, I was calling on you, Mike Gallagher. I'm sure you have thoughts both from the science and from the manager side, but yeah, how do you see this kind of research applying in New Jersey pine barrens, for example?
Yeah, well, how about we talk about like Green Mountain and New York? I feel like I talk about the New Jersey pine barrens all the time, but I think this is really some nice foundational research in a new landscape that doesn't receive a lot of fuels research. And unfortunately, it's a little bit far from where I work and other researchers in the Northern Research Station who are in the fire group to work all the time. And so we're trying to do a better job of kind of reaching out, getting engaged with folks like Peter. And I'm really excited. This is some great foundational work. There's a proposal out of SUNY working with Green Mountain and some of our research team to use terrestrial laser scanning and to kind of, this will be a really good part of the literature review, using it on Green Mountain and some places in New York that they hope to burn as part of this Northeastern Forest Cooperative proposal if it gets funded. So I'm really excited to like see and be a part of work that's not just in the New Jersey pine barrens. But also, I guess I just want to share too that there's like people all over the country who are getting started with TLS right now, and I guess also that it's another reason I'm happy that the Northeast is better represented and Maine and New Hampshire are represented. So I just want to say that I think that's exciting. Peter talked about fire behavior. But Peter, how do you think that some of these differences might impact things like burn windows, or for prescribed burning in the spring or fall, like availability of fuels to burn, not just fire, like the danger, but what about how might this in fact impact the number of days or periods that you could burn in a prescribed fire? How would it impact maybe something like ticks that we're trying to control? And how does it relate to mesification and the reversal of mesification? So I think that everything you're working on here is really neat.
Thanks.
I'm just excited about it.
Good. Yeah, I mean, those points that you just bring up too, I feel like you can't even think about those things without also thinking about the forest management, right? Like if you're thinking about fuel breaks or managing for ticks or mesification or whatever, like I'm already kind of thinking about, so what's the thinning prescription you might need to open up the forest canopy to make those fuels available? Or how do you just think about that heterogeneity on the landscape of like some of your more open canopy sites might burn nicely, in early spring or whatever, but your closed canopy sites might not. And using, like John was saying this earlier, kind of using those dense canopies you can burn into, areas with high moisture of extinction. Yeah, I think that's all kind of tied together.
Yeah, there's this concept of green fuel breaks. And it's some, help, maybe this is a way to help find some of those sweet spots of when, you can actually use a forest as a fuel break, or maybe it just isn't as difficult to manage that edge where you've got that interface between these, two types of conditions.
Right.
Yeah, thanks for that input there, Mike. I've got one more question here from Maddie. Could a study of cellular structure and capacitance inform coarse woody material drying rates and influence on microclimates?
Can we tell that Maddie has studied wood structure? That's such a great question, Maddie. So the publication where I got that fuels drying graph is it's the fire weather handbook that the Forest Service put out. It's put out in like 1970, but they have really interesting stuff on that actually. And I feel like they talk about when fuels are sort of coming into equilibrium with their environment and think about long-term drying. I feel like the cellular structure really influences it when you're in really dry environments, or it's been, 2 weeks since you've had a rain event, and there's this water that's bound up, I'm sure you know this, in the cells, and like the little tiny pockets in places where there's high surface tension in the water can make it really hard for that water to escape into the environment. But then when you think about that too, influencing on microclimate too, if the moisture from that wood is like it's like a sponge, and it's like releasing moisture into the understory and influencing the microclimate, that's super interesting too. That's a whole study in itself.
I think that's interesting. There's been a lot of research, as Peter mentioned, on that, and I think I was impressed that Peter actually weighed his moisture sticks, because a lot of times we use these two metal electrodes in a fuel moisture stick to get an estimate of the fuel moisture, and there's some problems with that. It's good, but it's not really like research grade to do it that way. And so I'm really impressed. I've never actually seen somebody take fuel moisture sticks out and weigh them, because everybody plugs their little electrode laden ones into some meter that emails them the moisture content or something. So that was really cool. I think typically we use ash moisture sticks. At least in New Jersey, we've used ash. But Maddie, a really neat study could be just thinking about how the conversion of species, say from pine, which might be a more softwood, to something like I don't know, maple gum, how their moisture content patterns change might contribute additionally to mesification, or something like and burnable periods. We've talked about leaf litter, but also like the wood on the forest floor might have similar patterns.
Right. Well, we're getting close to the end of the time here. I just wanted to put a couple things in the chat here really quick. If this is the last session of our student webinar series, but we would love to continue on with one in the spring. We already have one student that would like to present next year. So if you or anyone would like to be involved in the student webinar series, I put some information about our website there, but also my email. And you can just hit me up at nafsehelp@gmail.com, and we can get something set up for next year. So thank you again, Peter, for your information. It's very insightful and very engaging afterwards with the other people on the call, on the meeting. So thank you, everybody, for attending today. I'm going to keep this open, and if anybody has any other comments or wants to continue on, we'll keep the meeting running here for a few minutes. But otherwise, I'm going to stop the recording, and then again, you can drop off if you want, or stay on and continue to engage with Peter. So thank you again, everybody, and thank you, Peter, as well, for your presentation.
Yeah, thank you all.
Thanks, Peter.